A very interesting component of DSSAt 4.6 is the seasonal analysis. With seasonal analysis, we can run the model for many years of weather data with different treatments. Each might be considered a strategy. And the strategy is the same for every year. The initial conditions are reset each year, which means that we cannot run a whole rotation for seasonal analysis. To do that, we would use a sequence. And for each strategy, after running the model, we can get the distribution of different different variables, like for instance yield. We can add economic data, the cost of different inputs or the prices of inputs and outputs, and get the distributions of income. Once we have the distributions, we will ask what is then the best strategy for this case. First of all, what we need to do is to create an experiment using the tool crop management data. We will see an example of irrigated wheat in Córdoba, Spain. So we start DSSAt 4.6 and go to crop management data. We will open an experiment that we have here. It's called UCCO 6411, and that includes different treatments from 1 to 10, and treatment 10 is rain-fed wheat in Córdoba, Spain, and the other treatments are irrigated according to different criteria. Level 1 or treatment 1 is irrigated whenever the soil water falls below 90% of the maximum stored water, while 10% means, or 10 means, that the irrigation will be applied whenever soil water falls down to only 10% of available water. That has been included in the simulation options. So within simulation options, we have 10 levels, and each of the levels have been changed by using automatic irrigation, automatic when required, and the threshold for this level is 90. If we go to level 2, the threshold takes a while, is 80, and so and so. If we go to level number 9, the threshold is changed to only 10%, and so and so. So they have all the levels, they have in common a simulation start date of September the 1st. In this case, 1964. Why? Because we have defined the weather data from Córdoba, and we are going to use 40 years of data for the simulation. The simulation starts on September the 1st, but planting occurs. We have just one level for planting, and is December the 1st, 1964. That is the planting date. So the model start running September the 1st. The conditions at planting, say the initial conditions, consider that the profile has little water. We have a shallow silty clay, so only 10% of available water is in the soil on September the 1st. that would correspond to the typical water content after the summer in Córdoba. Nitrogen contents are also very small. In management, we will be adding urea, a total of 150 kilograms of urea, 0 days after planting. That will be applied. As you see here, fertilizer is the same for all the treatments, planting is the same for all the treatments, the field is the same for the treatments, and the cultivar, let's see the cultivar. The cultivar is number 1, which is Manitou. So we have everything we need. We have defined cultivar, we have defined field, planting, fertilizer, and the simulation control that basically changes the threshold for which irrigation is applied. Okay, so once we have this seasonal fields, okay, look at this. This is the general form for this experiment. It is a seasonal experiment, so all the treatments will be applied for the whole data set. As I said, in the field we have chosen UCCO 6450. This is a weather file that has 50 years starting on 64. So once we have it, once we have this file, we can proceed and run the model, the seasonal utility for this case. So now we go to seasonal, click on seasonal, and then we have UCCO 6411, and we click on run, and we see that we have 10 different treatments, and we click on run the model, and the model will be run for 40 years for the 10 treatments. After some time, the simulations will be completed. We click on OK, and we click on analysis. Then the model will show a summary of the different treatments and the number of runs, the crop, which is Ceres wheat, and the experiment code UCCO 6411. The model has been run 400 times, 40 years by 10 treatments. We click on OK. Then we see the report of the seasonal analysis of DSSAt. We click on save to save that report, and then we see that here we can plot or view different variables. For instance, anthesis date would not be changing with the treatments, and we can either view the data, we can check on regressions of different variables, we can graph different types of graphs, a box plot graph, a cumulative function plot, or the mean variance plot. For instance, let's say for harvested yield, we click on harvested yield, we click on view summary data, and we have here for the 10 treatments the mean yield from over 5 tons to more than 3 tons in the rain-fed treatment with a decreasing value. The variance in general increases for the different levels. In general, this is better irrigated. This is best irrigated treatment, treatment number 1, while rainfed does not receive irrigation at all. And it shows the lower average yield and the highest variance, the highest standard deviation. We see also here the range of values, the minimum and the maximum values for all the treatments. Click on OK. Clicking on regression, we can choose different variables. For instance, we can plot the line maximum and the harvested yield, showing all. We see that there is a good relationship between maximum yield, between maximum leaf area index and yield. We can have a look at the residuals. We can apply this type of analysis to any of the variables that we have produced. Apart from that, we can see the cumulative for harvested yield, still the plots. This is the box plot. So we have here the different percentiles, the 0 to 25 percentile, the 25 to 75 percentile, and the 25 to 100 percentile. This would be the minimum value of the distribution, and this would be the maximum value of the distribution. Remember that treatment number 10 is a rain-fed treatment, while this is the best irrigated treatment of all. We can get other type of graphs, like the cumulative function. Here we have the distributions of yield. The one value would mean the cumulative probability 1 and cumulative probability 0 versus the harvested yield. It is interesting to compare the different distributions, because with the different distributions we will take our decisions. We can also plot the mean variance plot. The mean variance plot for each treatment the value of the mean and the variance of the distribution. We can see clearly here that the rain-fed distribution has the lowest mean and the highest variance. It is clear the worst result, the one that we obtain with the rain-fed treatment. Apart from the biophysical analysis that we can perform for the different variables that have been originated running the model, we can go to economic analysis. And in economic analysis, we can also plot the box plot, the cumulative function of the mean variance. One important thing here is that we can edit the prices file. Click here, and we see a table where we can modify the grain price, and we can also fix a mean value for the grain price, but we can also consider a standard deviation, which means that the model will take the grain price as an statistical as a variable with mean value of 300 and standard deviation of 16. In this case, we can change that to different values. We can assign a price to the harvest byproduct. In the case of wheat, would be the straw. We can use different types of variables for considering changes or variability in the prices. We change the base production cost for this example, $300 per hectare. In this case, $300 per ton of wheat is the mean price. The fertilizer cost, $0.08 per kilogram. The cost per application of nitrogen, €16 per hectare. The irrigation cost per millimeter of irrigation applied, 0.6, which means a cost of 0.06 dollars per cubic meter. The irrigation cost per application, 12.5. The seed cost per kilogram, or the cost of other components, organic amendments, P fertilizer or K fertilizer, which have not been used in this example. Once we change any of these values, for instance, we could choose to put 0.1 for the harvest byproduct, we can apply to all treatments. We're gonna return it to 0 as it was, and then apply to all treatments. When we are happy with that, we click on OK, and then we can save the price with the same experiment name with the extension PRI. We click on yes, and then we click on save. Now this data will be used to calculate the incomes for the different years. We can see the box plot of income would be dollars per hectare for the different treatments considered. Now we see that the best, remember that the strategy number 1 gave us the highest yield. However, it does not produce the highest income. We can also check on the cumulative function plots, and here we have the different strategies with different color. Now we will discuss what are the meaning, how can we compare strategies using the cumulative functions. We can also check on the means variance plot, and we see here that the strategy number 10 has basically or practically the lowest income and the highest variance. On the other hand, treatments 6 or 7 have the highest mean value of income with the lowest variance. So in principle, those would be the best strategies. In strategy analysis, we see here a table that gives us for each of the treatments the expected value, means the mean, and the expected value minus the Gini difference. We see here a column that says efficient, and we see that the strategy 6 is marked as efficient yes. That means that this strategy has the highest value of expected value and the highest difference with Gini difference. So that would be the best strategy of all. Let's review how can we compare different distributions. The 4 criteria that are present in DSSAt 4.6 are: first, the means variance, then the first order stochastic dominance, second order stochastic dominance, and Gini criterion. The mean variance criterion is only valid for when we are comparing normal distributions. We can say that A, the strategy A, dominates strategy B if the expected value of A, the mean of the A strategy, is equal to the mean of the B strategy, but the variance of A is lower than the variance of B, which means that A dominates B if the average is the same, but the variance of A is lower than the variance of B. But this mean variance criterion can also be stated that the A dominates B if they have the same variance, but the mean for the expected value for A strategy is greater than the expected value for the B strategy. If we look at the graph of the mean versus variance for the 10 treatments of the example, we see that if we compare strategy 1, which is irrigating for a 90% threshold, with strategy 10, which is a rain-fed crop, we see that their average, the mean, the expected income, is basically the same for the two strategies, but the variance for strategy 1 is much lower than the variance for strategy 10. So we would choose this strategy over this one, using the mean variance criterion. The second criteria to consider is first order stochastic dominance. We say that strategy A dominates strategy B by first order stochastic dominance if the cumulative distribution function of A is always lower than the cumulative distribution function of B for all values of income. Take for instance the cumulative probability versus income for the different treatments. In the example, we see here, we compare the rain-fed treatment, which is this brown one. We compare it, for instance, with the treatment 20, which is this one. We see the treatment 20 is always below the rain-fed treatment. That means that the 20 treatment presents first order stochastic dominance over the rain-fed treatment. Why? Because it is always lower than the rain-fed treatment. In the case of second order stochastic dominance, a treatment A dominates over strategy B by second order stochastic dominance if the G function of the treatment A is always lower than the G function for the strategy B for all X, in this case for all values of income. G is the integral of the cumulative distribution function. Going back to the example, we would need to calculate the integral of these curves below the integrals of this the integral below these curves for the different strategies, and we would compare those integral functions for the different treatments. But this is not required if we already have differences in first order stochastic dominance. This would only be necessary if there are not differences, clear differences in first order stochastic dominance. The last criterion, if the other criteria have not worked, is the mean Gini criterion. With this, the strategy A dominates strategy B if the expected value of A is greater than the expected value for B, and the difference expected value minus gamma of this treatment is greater than the difference expected value minus gamma of B. And the function gamma for a treatment is equal to half the Gini mean difference. And the Gini mean difference is the absolute expected value of the difference between two random values. In other words, it's the mean absolute difference. Going back to the example, in the strategy analysis, we see the table with the different treatments and the expected value and the difference and the calculated difference. using the Gini means difference. And we see that there is a strategy that has the highest expected value and has the highest difference between expected value and tau and sigma function. So it is marked as efficient. That would be the best strategy. In summary, in the example that we have seen about irrigating wheat using different thresholds for applying irrigation versus not irrigating, like this one, we see here, using the economic data in this example, the mean values and the standard deviations of the different strategies. In principle, the best strategy would have the highest mean and the lowest variance. We see that treatment 6 and 7 are very close. They have almost the same variance, and it's a little higher for treatment 6. But the variance is a little smaller for treatment 7. What is best from these two? Let's see the cumulative function plot only for treatment 6 and 7, which are thresholds of 40 and 30%. The distribution functions are really not superior for any of the two, because we see here that some red data are above the green, although the green is usually above. So it looks like the green, the 30%, would be better than the 40%. But clearly, when we apply the Gini criterion, in this case, comparing 6 and 7 tell us that the treatment number 6 is superior over treatment number 7 because the mean value is greater and the difference of the mean minus the Gini function is greater for 6 than for 7. In other words, the best strategy in this case would be irrigating with a threshold of 40%, which is strategy number 6.